Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all for the next lecture in this particular course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. We have been seeing in the previous class on the electroanalytical methods, and we were discussing on the aspects related to the cyclic voltammetry, and let us continue with that aspect of it. We were talking about the reversibility and irreversibility. I talked to you the reversibility features that you should be able to see, both the peaks, and the difference between the peaks should be 60 by n, the ratio of the current should be close to 1, and if any of these parameter is not there, then that becomes a irreversible category called quasi-reversible. Let us not worry about those aspect of it. Let us look at some example here is shown for a cobalt CP DPPA complex. It is not very essential for you to know all those ligands. Essentially it is a copper cobalt based complex, and what we wanted to basically look at in this is that this gives the redox waves here. So this is called one couple, this is the other couple. There are two couples are involved in this particular reaction here. So that means one electron, again one more electron, and back again reversibility is there, and you can see both the peaks here very well, and the ratio of the current, if you check, it will become 1 and are close to 1, and therefore they are quite reversible. So this has a 1 electron kind of thing, this green trace of this. Now that is done under the nitrogen atmosphere. Now if I allow the oxygen atmosphere in the medium, then what will happen is it will go to only one peak of it and then almost nothing, and then it is absolutely become reversible. Why is it so? So all the change you have done is not in the potential, not in the current, none of the things, not in the electrode, but only the atmosphere present in the reaction medium. So one is the inert like argon or nitrogen, etc., and the other one is air which contains the oxygen. So that means oxygen is doing something that you need to think in terms of that. So you have initially what you have done was you are increasing the negative potential, that means you are reducing. So the first electron transfer will reduce the species, and this reduced species now reacts with the oxygen, and reduced species has an extra electron. This electron is transferred to the air or oxygen, not air, oxygen, and therefore there is a chemical reaction is going on into that. So therefore that particular species is no more available there. So the species, the 1 electron reduced species is no more available, and then the chemical reaction has taken place. So in the reversible there is no reversibility. In the reverse, it does not find the species required to reoxidize. So earlier you have 1 electron reduction, you also have 1 more electron reduction, then you reverse back with the oxidation and 1 more oxidation get back. So both the cycles and both the couples are reversible electron transfer kind of things. So this is, you can see, an irreversible kind of things. When the species that you have reduced or oxidized initially, if that is not available back for the reoxidation or re-reduction, that means something has happened to that species. So that means there is some kind of a chemical reaction happening. So then obviously you have no reversibility coming into the thing. So this will be affected more when the electron transfer at the surface is slow compared to the molecule or species transport. That is called mass transport. So the mass transport into that. So then in such cases, if there is some reaction is occurring and the molecule, the species is not coming back to the thing, the species of the reduced one is not coming back to that, then you will have a reversible, irreversible kind of thing. So electron transfer is done very fast, but then there is some kind of a chemical reaction. These things will make the process reversible. So that means we have electrochemical reactions which can be termed as a simple, which can also be termed as a complex. So simple means you have a species like iron 3 plus that flows to the electrode surface and then picks up an electron, becomes the iron 2 plus, finished. Nothing else is happening. So again reversible kind of. So simple electron transfer from your electrode to the surface. Now, so the same thing for copper also here. For the copper, you're talking about 2 electrons, then become copper 0 gets deposited. These kind of processes are called the simple electron transfer. On the other hand, you see on the right side here, this is the nitro, so para-iodonitrobenzene or para-nitroiodobenzene, either way. And this, when it approaches the surface, it receives an electron. So there is a electron transfer is taking place. Obviously, that electron transfer taking place, which means the reduced species is not, can undergo a chemical, because it can undergo deiodination, and that means it loses the iodine. So therefore it becomes nitrobenzene. Or it can take sequential number of electrons like 1, 2, 3, 4, 5, and protons can become the nitro can become the amine. So nitro is NO2 group, the NH2 group, NH2 it has to become, and that is where you have the electron transfer occurring. So this is kind of reactions are called complex reaction, because the species which is first electron is not available at the surface because it undergoes some chemical reaction. Even whatever little is available, it may undergo quickly additional electron transfer reactions. So these kind of things is referred as the complex electrochemical reactions. So now we have looked at the electrochemical reversibility, then we have looked at the electrochemical irreversibility. So what basically means is that these processes, suppose you have a species which referred as ox, which means oxidized form of it, and if it takes an electron, then it will go to the reduced species. Now this is the first electron transfer reaction. This RED species, reduced species, if is available at the surface, it should go back to that. So if that is undergoing some kind of a reaction, you can see that. So it's going through some other process. So this is is giving rise to, so you have the reduced species, and in this reduced species is giving some other kinds of species here, and the rate of reaction that you have. So this is this is a chemical reaction, this is a electrode reaction. So this occurs as an electrode, and that means this species is not available sufficient enough or not available at all. So that is what you are looking at. So that depends upon the rate of this conversion. So this is a chemical reaction. So this reaction, so you can look at in terms of the electrochemical is R and chemical is I. So R refers to reversible and I refers to irreversible kind of a process that you're looking at. So that means reversible electron transfer followed by an irreversible chemical reaction. So chemical reaction is not irreversible, the electron transfer is there. So that depends on what? K. So the rate at which. So if the K increases, that means the conversion of this first reduced species transforms to the product very quickly, that means not available at this particular thing. Okay. So very little amount or no amount of reduced species is available. Now how will you try to control this, to look at the process what is going on? Now you have something called scan speed, speed at which you vary the potential. If you can change that potential at different rates, scan speed can be controlled. So you go from smaller, lower to higher to higher to higher. So what happens? Higher means the electron transfer process, you are pushing it quicker as compared to that of the chemical process. Therefore there is some amount of species available, and at very high rates a lot of species available, so you can get back to this. So get back to the reversibility. So this is one. In the other case, you have initially a chemical reaction. So that means you have put your electrodes, you have taken, there is a chemical reaction happening, and that going to oxidized species. This oxidized species is basically taking electron reduced. The first one is a chemical reaction, the next one is an electrode reaction. Okay. So this means this oxidized species is available for the reduction at this particular electrode surface. Okay. So this basically depends upon the equilibrium constant of the first species. How much is there, the oxidized is available, etc. So therefore this is a chemically irreversible but electrochemically reversible kind of thing. Reversible chemical followed by reversible electrochemical, both. So CRER. Okay, both reversible kind of things. So this depends upon the equilibrium constant. Okay. So the extreme case, the equilibrium constant is so large that the reaction is considered as basically irreversible, and then the CV becomes reversible. Okay. So the equilibrium constant rate can be extracted from such kind of a CV data. So therefore you have reactions where the equilibrium constants are lower, equilibrium constants are higher, or where you are looking at those kind of things. So you can work out the rate processes can be derived. Now we look at some electrochemical reactions, reversibility to irreversibility, irreversibility to reversibility, different kinds of mechanisms. Shown 3 examples. So this first one is the ER, means electrochemical reversibility, and CI, this is the one. So this one can be worked out by changing the scan rate. So what do you do? Because here is the electron transfer reversibility, chemical is irreversible, and you initially do, for example, at a lower rate 100 millivolts per second or 0.1 volts per second, and that is where this one green, and no, initially 0.1 is at the red, and then 1 volt per second inverse is a green, and then you make 10 volts per second is this blue. So if you see that red one has only one side peak, very little, green one had go a little bit on the reverse side, but not current ratio will be the same, and not even the difference in the potential as well will not. So it's not reversible. Red one is not reversible, green one is not reversible, but now blue one is reversible, because you are not changing the molecule, you are not changing the analyte, you are only changing the rate at which you are measuring the voltammogram, that is the potential sweep that you are making. So the scan rate becomes so fast, so it can become the reversible kind of thing. That means it is capturing the species which is formed at the surface before it diffuses, before it chemically gets converted to that, and that is where the thing is. So second example, so that means this can be made reversible by changing the scan rate to high. So from irreversible to the reversible. So the next example is the CR and ER. So both are reversible, and this can be made by changing the by varying the rate constant. If you can change the forward rate constant of the CR step, then the more the reversible is that. So initially you have a rate of 1, and that is with the blue here. You see the maximum peak here, a little peak here, then 10, the rate constant is per second, so that is 10, and then you have the next one dark green, and the 100 rate constant light green, and then 1000 you have red. So when it comes to the red, all more or less coming close towards the reversibility. So here the reversibility can be adjusted by changing the rate of the rate constant of the reaction. So by changing the rate constant of the reaction, you can manage by getting that one. And the third one is the third one is the 2 steps of ER. That means electrode reaction reversible, electrode reaction reversible. So that means you basically have a 2 reaction, 2 couples, and then you are talking about the reversibility of these ones. And so if the difference between this E half of 1 and E half of the 2, let us say, so if this difference is smaller, obviously there will be overlap, or 0 means completely overlap. If it is little smaller, little separation. If it is more difference, then you will have a greater separation, and then you can see the two peaks separately. So, as the delta E half, the difference between the two potentials of the two waves, that peak separation, as it increases, then you will get both the peaks separately. Otherwise, both of them come into one, and that becomes the 2 electron process instead of 2 1 electron process. So, you can get by increasing. So, separation between the two steps. So, that is where important point in this is. Now, we have seen the irreversible reactions going towards the reversibility of that. Let us look at some. For example, here there is a ligand in this, and there is a copper 2 ion. So, if you just look at the ligand electrochemical process voltammetry, almost no good peak at all. Now, if you put the ligand plus the copper, you can see, so you get a nice, of course it is not reversible, but shows that there is a complexation taken place between the copper 2 ion. You take a copper 2 salt like copper 2 chloride and this ligand and mix it, and you get your thing. Now, how do you make that into the reversible kind of a thing? So, how do you find what kind of a process is going on? So, it is basically diffusion control. So, diffusion control can be adjusted by changing the, making it a scan rate change. So, here the scan rate change going from 10 millivolt up to 320 millivolts, so around 30 times. So, by going into 30 times, you get completely reversible kind of a peak, and that tells this is a diffusion control kind of thing. Now, at each stage you can have the current ratio, and then from the current ratio you can explain the ratio of the IPC, IPA versus IPC deviates from 1, and this observation with this scan rate, you can change the gap between these two. So, you can make it more reversible type, and this is a diffusion control kind of a example. So, I hope that is clear to you. So, by changing the scan rate, you can find what kind of reaction, why this is irreversible, because of the diffusion control kind of a process that is happening. Okay, that was the inorganic example. We can take even organic level example. So, what you are taking here? You are taking here a para-nitrazophenol, and you start from here. So, you keep going, nothing, no current change at all. So, you are going from somewhere plus 0.2 towards 0. That means you are in the decreasing direction, that means you are reducing the things. So, that one, and at this stage around minus 0.0304 starts picking up the current, and then you can see that it is increasing. Then when you reverse back, yes, you will get, but very little of the current, not much of that. And then you go further, then you get a good peak beyond plus 0.2, and then when you continue the second scan, you get one more peak here. So, what is this happening? So, initially this particular peak comes from the first reduction of this one. This is reduced essentially in a 2 electron kind of thing, and your nitroso would become the hydroxylamine NHOH kind of thing. So, this is what you find. But when you are reversing back, you do not have much of the species available at that species converts chemically into this one. So, from the phenolic form to the keto form. So, the quinone form. So, you have a semi-quinone form with this imine kind of a species. Okay, and so that is where you have in the solution you have a little bit of this, and you have also this kind of a species will be there. So, a small amount of reoxidation you would see here. And now, if you further go here, what is happening? So, what is happening is you are going in the positive direction, you have a oxidation peak. So, that means whatever is there in the bulk, this particular species, now this species will go into oxidized form of it. And now this oxidized form will get re-reduced here, you can see. So, this peak is a re-reduced of this one, and this peak is an oxidized form of this one. Okay, and this is 1 electron transferred into whatever the species that you have in some intermediate kind of thing. So, now I hope you have, so you have an electron transfer first, chemical reaction, and this is electron transfer. So, therefore, this is called the E electron transfer, the chemical electron transfer, ECE kind of a reaction that you have seen. Okay, I hope that example is also clear to you. Okay, some application side, for example, when the wine making process, they use sulfur dioxide. Okay, so this is added to prevent certain unwanted reactions basically, but there are some side effects because these sulfur dioxide in the dissolved form can get oxidized to sulfites. So those sulfites are harmful to the body. So one needs to know how much of sulfite is there, etc., whether they have been able to remove the sulfite completely from that wine. So these are the things. This can be studied by the electrochemical cyclic voltammetry reactions. Now you see that a solution of that particular the wine having different percentages of are made as a standard solutions. 20 ppm of sulfur dioxide, 40 ppm, 60 ppm, 80 ppm, 100 ppm. You can see that 1, 2, 3, 4, 5, 20, 40. So you can see the extent to which the sulfur dioxide is present is reflected in the current area, the current value of this. So that means if you measure the current in this particular kind of a voltammetric scan, then you can get the amount of SO2 being present there. Okay, and this can also be done to find the sensitivity by changing the different kind of electrodes. Okay, so you have a silver electrode is giving sensitivity somewhat low. You have a gold electrode which is showing slightly gold on silver, and you have a mixed kind of an electrode and which is giving higher. Okay, so there is electrode consisting of gold nanoparticles mixed with the silver which shows the highest sensitivity. So therefore one can use this to get the maximum current possible for even for a low amounts of the sulfur dioxide being present. So this particular part is a standardization or normalization kind of thing. So here you have other curves wherein you can use different medium with the 20 ppm of SO2, 60 ppm, 100 ppm, and even in the caffeic acid in presence of some other materials. Some other materials are also possible in the wine process. So you should not have this peak being disturbed, and this peak is not disturbed even in presence of the thing. You can still measure that one. And even if you add some other compound like this is the acetaldehyde, this is one which quenches the SO2 which is present at sulfites. So therefore you can see that the peak is lost. This peak is because of the sulfite, and when you add this component of acetaldehyde, this particular thing is being quenched. So therefore you can see the difference in that. So from that difference you can talk about how much of the sulfite or sulfur dioxide is being present. So analytically you can quantify as well. You can also detect this is coming from the sulfur dioxide. So you can detection as well as the quantification can be done. So for example, when you take complexation, again some parameters. What are the parameters that you have? Potential at which EPA, EPC, difference in the potential, ratio of the current. These are some of the parameters that you can be. So if you take the iron 2 plus iron 3 plus couple which is shown here and showing that, and in presence of the DMSO, this dashed curve, and in presence of the xylitol is the carbohydrate which can bind with that to the iron, and then you can see the peak heights, current heights are changing, the gap, the separation between this, and which is a characteristic of the complexation. So from this experiment what you can say, you can tell that the iron 2 plus is now complex with that ligand. Okay, so this is with the xylitol, this is with the glycine. So this is the iron means not just the iron salt alone, you can see very nice, reasonably good peaks. Now you put 1:1 glycine for this. So if you put the 1:1 glycine, this is with the dashed line here, you can see that, you can see very somewhat nice, and then you put the 4:1 the glycine, 4 equivalent to the glycine with this, you can see it. So there is some amount of complexation and much greater amount of complexation. So you can also quantify the extent of complexation occurred because these parameters are differing. There is a more irreversibility is found when the complexation occurs. Reversibility is coming from non-complex species. Irreversibility is coming from the complex species. So that means cyclic voltammetry experiment can tell you that the metal ion is complexed to partial extent, to greater extent, to complete extent. So all those things can be quantified also to what extent of the complexation is occurred. So these are the things. So we have another example here, organic, where this kind of a ligand binding to a copper, can give different kinds of species in different anions or solvent. Here CF3SO3, so here you have a 6 coordinated one, and when you have the NO3 nitrate instead of trifluoromethyl sulfonate, you have a nitrate, then it gives more of a 5, but it is also fractional behavior. And when you go to the instead of these anion, you have a 2 bromine ions, again 5 coordinated, but this 5 coordinated species can undergo the fractional behavior, can go change to 6 with the solvent or go to 4, etc. So all these things. So that is why you're trying to find, you're finding more peaks on the reverse direction. You have a copper 1 to copper 2, but you have extra peaks coming up here, because these are all again the copper 2 to copper 1, but in different environments. It could be a coordination environment, as well as whether there is a solvent molecule, not solvent molecule, or more than one solvent molecule. All of these are giving. And on this extreme end, you have the ligand getting oxidized. In all these cases, that we will not basically differentiate. Okay. So complexations, variation in the geometries, number of ligands, all those things can also be identified. Now you have a complex of this. M is one time is copper, other time is zinc. You can see when you, and this is added to the DNA, and look at this cyclic voltammetry. The A is as it is, B is when added to the DNA. The changes are very minute here. Here you can see. But whereas when you make the zinc complex, the changes are dramatic here in the current and the separation, everything is correct. So that means the zinc complex is binding much more strongly to the DNA helix by the groove binding kind of a thing. Okay, both of them are binding. The copper the complex is binding to a very little extent, whereas the zinc complex is binding to a greater extent into these ones. So other details you can read. I have also given the reference if you want more details, but not required as far as the electrochemistry experiment is concerned. So therefore voltammetry can be used for binding whether this compound is binding to the DNA or not binding. You can also get some other kinds of things. You wanted to determine this particular the drug citalopram, CIT. So what is done in this experiment is this particular electrode is coated with kind of a material which is composite material having the gold nanoparticle, multi-wall carbon nanotubes, etc., and then put this particular kind of a material to make for conducting the electron part of that. So it's a basically modified with this is the manganese based metal organic framework, and then the carbon nanotube and gold the nanoparticles. This together is put. So when you put this, and you can get very nicely the voltammogram for this particular molecule. This particular molecule undergoes a 2 electron oxidation from here. Minus 2 electron means oxidation, and that gives them. So this peak current you can use for the concentration. So that means you can quantify that. So a lot of experiments were done and found out there is a linearity in this range, linearity in this range, this range. So it is the electrode not in pure form, electrode which is coated with this particular composite material is the one which gives this kind of a nice profile of the voltammogram, where you can integrate the current and then use that one. Okay, so redox potentials of this, I am sure you are aware at different ranges this redox potentials happen. This is what you study in the basic electrochemistry course whenever you study. And the lithium is the oxidation potential is very high, means reduction potential is very reverse exactly. And the minus means the reduction is less favored, oxidation is more favored, and that's where exactly you can take all of them. Okay, here is an example of organic moiety here. So this organic moiety R group you are changing. So change the R group to nitro, to cyano, to CO, etc. You can see what is happening. Your redox potentials are changing. So therefore, by looking at these potentials, you can explain that particular molecule, what kind of a group that is being present there. So basically the redox potential range will always help. For example, if you look at this, this is minus 0.7, this is plus 0.0, that means this reduction of this is more favored than this one. Or if you look at between these two, plus 0.4 and minus 0.7, this reduction of this is much more favorable than this one. So like that you can always find which of the species are more easily reducible, which of the species are more easily oxidizable. Similarly, VO2 with the 5 plus to 4 plus redox potentials. So this all gives a idea of some redox potentials, etc. Not only that, you can extend this to biological systems. This is a metalloprotein, copper metalloprotein, having some amino acids nearby. So if you change this amino acid from this histidine to cysteine, methionine, aspartic, etc., the structures are shown here, their redox potential change. So some of them become very negative, some of them become positive, and you have a range. So that means you are tuning the potential of the particular, in this case it is iron sulfur protein, and is this particular group which you are changing. You can also change this group. Both of them will influence the redox potentials of this, and that is what is shown over here. Example, so histidine to cysteine, the lysine to cysteine, the aspartic to cysteine, and the normal one, wild one, etc. These are all going. So that means by using the cyclic voltammetry, you can basically find out what kind of environment is changed with respect to the metal center in the metal enzyme. Okay. So this is just for you to get a practice, and suppose given this kind of a voltammogram, try to find out the oxidation potentials, reduction potentials, oxidation current, reduction current, find out the reversibility, irreversibility, all of those, and make your points basically in this. With these two classes, the previous one and this one, I try to close this topic of the electroanalytical techniques or electrochemical techniques, and we will go into a new topic in the next upcoming class based on the analytical techniques. Okay. Thank you very much.